230 meters below the surface of the North Atlantic, off the southern coast of Greenland, something is hiding. Not hiding badly, hiding perfectly. A diesel-electric submarine, roughly 4,000 tons of steel, batteries, and patience, has killed its engines, vented its ballast to neutral buoyancy, and settled into a specific depth band like a man lying flat on a shelf. It is making less than 4 knots on electric drive, virtually silent, and it has chosen its depth with surgical precision. Because at 230 meters, the physics of cold water does something extraordinary. The ocean around this submarine stops behaving like a medium and starts behaving like a mirror. And this crew knows exactly what that means. This is a hypothetical scenario, built from real capabilities for education and entertainment. But every piece of the physics you are about to see, every number, every mechanism, is real. Here is what no surface ship above knows yet. There is a NATO sensor field 6 nautical miles to the north. A string of bottom-mounted hydrophones laid across a deep water channel, part of the undersea surveillance architecture that monitors this stretch of ocean. The submarine is moving toward it on battery power at a walking pace, betting that 3 stacked thermal boundaries between itself and the surface will scatter every sonar ping aimed at it before those pings get anywhere close. For a diesel boat that costs somewhere north of $300 million, it is a remarkably elegant bet. And for a few minutes, it is winning. The sub's advantage will not last. Somewhere in this water, there is already a weapon that does not need to ping from the surface. A weapon that will swim down into the same thermal stack the submarine is hiding inside and search from within. The question is not whether it finds its target. The question is what happens in the 4 minutes between launch and intercept, and what the Virginia-class submarine hunting this boat is actually trying to accomplish. Because this story does not end with a detonation. It ends with something more valuable. To understand the trap this diesel submarine has set for itself, you need to understand the physics it is exploiting. Start with temperature. The North Atlantic off Greenland is not a uniform column of water. It is a layered system. Cold surface water, slightly warmer intermediate layers, colder again at depth, and at each boundary where one temperature zone meets the next, something happens to sound. Sound travels faster through warmer water than cold. So when a sonar ping moves from a warmer layer downward into a colder one, it bends. Not randomly, predictably, toward the colder water, curving away from vertical and back up toward the surface. Think of it like light bending through a prism, except the prism is invisible, is a kilometer thick, and moves with the season. In this patch of water right now, there are 3 distinct thermal boundaries between the surface and 200 meters. Each one acts as a partial reflector and a redirector for acoustic energy. A sonar ping fired downward from a surface ship hits the first boundary and bends. The portion that passes through hits the second and bends again. By the time any significant acoustic energy reaches the depth where this submarine is sitting, it has been scattered into a diffuse haze arriving from the wrong angle, attenuated, partially reflected back upward, partially refracted sideways. The submarine's hull does not even need to be acoustically quiet, which it is, because the water itself is doing the hiding. This stack of thermal boundaries is what submariners call the layer cake, a diesel-electric boat running on batteries, producing almost no mechanical noise and no thermal signature, sitting motionless inside the deepest layer, is as close to invisible as physics allows. Detection range for a surface ship's active sonar in these conditions collapses from a theoretical 20 nautical miles in open, isothermal water down to under 2 nautical miles. Sometimes less. The math is brutal. The submarine knows this. That is why it chose this depth. That is why it chose this season. And that is why it is moving, slowly, deliberately, toward a sensor field that monitors NATO's northern flank. Here's what strikes me about this scenario every time I study it. The submarine crew has done everything right. Their tactics are textbook. Their physics is real. The layer cake is not a trick or an anomaly. It is a fundamental property of cold northern water, predictable, repeatable, exploitable. They have stacked the odds in their favor with nothing but patience and geography. And yet they are already in trouble. They just don't know it yet. 22 nautical miles to the west, a Virginia-class submarine runs deep and quiet on its own. This boat carries no exotic magic. It is not using some classified sensor that ignores thermoclines. It is operating within the same physics as everything else in this ocean. But it has 2 advantages the diesel boat cannot overcome. The first is that it has been tracking this contact, this faint, intermittent acoustic whisper, for the past 90 minutes. Not through active sonar pings, through passive listening. A Virginia-class boat at slow speed on electric drive is one of the quietest large objects ever built by human hands. It does not announce itself with active sonar unless it has to. It listens. And what it has been listening to, across 90 minutes and 20-plus nautical miles of cold water, is the diesel submarine's battery-powered electric motor. A faint 60 hertz hum, barely distinguishable from ocean noise, but consistent, directional, and growing slightly as the target moves north. The second advantage is what the Virginia is carrying in its torpedo tubes. A Mark 48 ADCAP torpedo, advanced capability, is not a dumb projectile. It is a guided weapon with its own active and passive sonar suite built into the nose, its own onboard computer, and a wire. Literally a wire, spooled out behind it as it runs, that connects it back to the firing submarine for the duration of its run. When a Virginia fires a Mark 48, it is not throwing a spear. It is deploying a remote-controlled hunting system that can search independently, receive course corrections from the parent submarine, and make terminal engagement decisions on its own once the wire is cut. It runs at over 55 knots. It carries a warhead size to defeat a double-hulled submarine, and it can dive. That last detail is the one that matters here. Because the layer cake that is hiding the diesel submarine from surface ships, from helicopters, from sonobuoys dropped from a P-8A Poseidon patrol aircraft circling high above, from the hull-mounted sonar of any surface combatant, does not hide the diesel submarine from a weapon that enters the water column and descends through every thermal layer from the inside. Think of it this way. Imagine you are trying to spot a fish hiding under a series of glass panels submerged in a tank. From above, each panel reflects light back at you, and the reflections stack. By the third panel down, you cannot see anything below. Now imagine, instead of looking from the top, you lower a small camera through the panels, one by one, until it is in the same layer as the fish. The glass panels are still there. They still reflect. But your camera is already past them. It is looking horizontally at the fish's depth, in the fish's water. The thermal boundaries that made the fish invisible from above are now behind you. The fish has nowhere to hide. That is the Mark 48 ADCAP's core tactical advantage. Not speed, not warhead size. The ability to enter the water at one depth and hunt at another. The Virginia's fire control team has been building a solution for 11 minutes. In submarine warfare, a solution means a continuously updated estimate of the target's position, depth, course, and speed, precise enough to put a torpedo where the target will be, not where it is now. The diesel boat is at approximately 235 meters depth, making 3.8 knots on a heading of 015 degrees, and it has not changed course or speed in the last 40 minutes. It is focused on its objective. It is not listening for threats from the west because it believes its thermal shield makes it undetectable from any direction. That confidence is understandable. It is also fatal to the mission. The Virginia's commanding officer makes a decision that reflects doctrine developed over decades of cold water anti-submarine operations. Do not alert the target. Do not ping. Do not let them hear the torpedo launch transient if it can be helped. The launch is a soft start sequence, tube pressure equalized with ambient sea pressure before the weapon ejects, minimizing the acoustic spike of firing. The Mark 48 enters the water. Wire out. Running. 55 knots. Depth. Launch depth. Matching the Virginia. The torpedo's own sonar is passive at this stage, listening, not pinging. The wire transmits real-time data back to the fire control team. Speed, heading, depth, bearing to target, confidence level on the acoustic contact. The operators watch a display that looks, functionally, like a video game. Except the consequence of a mistake is a $300 million hull escaping with a recorded acoustic profile of your approach. At this point in the run, the torpedo is crossing the thermal layers. First boundary, through. Second boundary, through. Third boundary, through. Each crossing takes less than 2 seconds at this speed. The torpedo's nose sonar, now active, pinging in a narrow forward cone, registers the acoustic environment changing as it descends. Warmer. Slightly warmer. Colder. The layers are real. The torpedo logs them and keeps running. The diesel submarine's crew hears nothing yet. They are running their own passive sonar suite, a capable system designed to detect the broad-spectrum noise of surface ships, helicopters, and active sonar pings from above. What they are not built to hear is a torpedo running at speed from the west, below the layer they thought was their floor, in the same thermal zone they chose as their refuge. Here's the question that matters right now. With the torpedo 30 seconds from active acquisition range, does the diesel submarine have any move left? The honest answer is, maybe one. But it requires them to know the torpedo is coming before it starts pinging, and the window for that is closing at 55 knots. Here's where things get complicated for the Mark 48. At 235 meters, in cold water with slight biological noise from deep scattering layer organisms, the passive acoustic picture is cluttered. The diesel submarine's electric motor hum is there, but the bearing resolution at this range, now under 2 nautical miles, is smeared by multipath propagation within the deep layer. The torpedo's computer flags the contact as lower confidence than the Virginia's fire control team would like. The operator on the Virginia has a choice. Go active now and give the target several seconds of warning, or hold passive and risk the torpedo running past without a firm solution. He waits 4 seconds. Then he calls active. The torpedo's nose sonar emits a single tight beam pulse. Not the broad hemisphere sweep of a ship's hull sonar, but a narrow, forward-directed cone optimized for close-range discrimination. The ping travels through the deep layer horizontally. It hits a curved steel hull at 240 meters. The return is immediate, clean, and unambiguous. The diesel submarine's sonar operator hears it. 1 ping. Close. Very close. From below and ahead. From inside the layer. The next 3 seconds are the most important in the entire engagement. The diesel submarine's commanding officer has 3 options, and he knows them all. He can go to full power and run. But a diesel boat at full speed on batteries makes dramatically more noise and will be heard by every passive sensor in the area. And at 55 knots, the torpedo closes at roughly 1,400 meters per minute. Running buys time measured in seconds, not minutes. He can release a torpedo decoy, a noisemaker that mimics his acoustic signature. But the Mark 48 ADCAP seeker is close enough now that it can discriminate between a moving hull and a stationary emitter by Doppler shift. The decoy might buy 1 or 2 seconds of seeker confusion. He can maneuver hard, turning perpendicular to the torpedo's approach to complicate its targeting geometry. But at 3+ knots starting speed, a 4,000-ton boat does not turn fast. He does all 3 in that order. Emergency power. Decoy released. Hard turn to starboard. On the Virginia's fire control display, the torpedo's track shifts, correcting for the target's acceleration, dismissing the decoy's return based on its static Doppler signature, adjusting for the turn. The wire is still connected. The operator can see everything. He can intervene. He chooses not to. And here is where the doctrine this entire mission was built around takes over. The Virginia does not want this submarine destroyed. Not today. Today, the prize is something more valuable than wreckage on the seafloor. The prize is a complete acoustic signature. The diesel boat's full-power electric drive profile, its battery discharge signature, its pump frequencies, its flow noise at speed. A signature recorded at close range, from multiple angles, in real operating conditions. A signature that goes into a database, that lets every passive sonar system in the NATO inventory recognize this specific hull the moment it enters the water anywhere in the world. Forever. The operator does something unexpected. He commands the torpedo to shallow. The Mark 48 pulls up sharply, ascending 30 meters in a matter of seconds, crossing back through the thermal boundary, and runs a deliberate close pass. Not a detonation, a pass. 50 meters off the diesel submarine's port flank, moving fast enough that the pressure wave is felt inside the hull as a physical thump, like someone hitting the outside of the boat with a flat hand. Hard. Then the Virginia transmits a single active ping from its own sonar. 1 pulse. Powerful. Directional. Aimed directly at the diesel submarine from the west. The message is not acoustic. It is tactical. It says, "We know where you are. We have known for 90 minutes. Our torpedo was inside your lair, and we chose not to use it. You have been recorded. You have been pinned. And you are now 4 miles from a sensor field you were hoping to approach undetected, with a Virginia-class submarine on your quarter and a Mark 48 in the water. I will say this plainly, even if it is unpopular, the deliberate close pass instead of a detonation is the correct call, and it is also the harder one. A Navy that chooses a recorded signature over a confirmed sinking is operating at a level of strategic patience that most people watching this story will find frustrating. But a $300 million hull on the bottom of the North Atlantic is intelligence that is over and done. A $300 million hull that knows it was caught, that surfaces and goes home carrying the knowledge that it was detected, tracked, and deliberately released. That is a message delivered to every admiral in the chain of command above that crew. The layer cake did not work. And they know it. The diesel submarine blows its ballast tanks. Not slowly. Emergency surface. Compressed air rams seawater out of the ballast compartments, and the boat rises fast, breaking the surface in a welter of white foam and displaced North Atlantic swells. On the Virginia's acoustic sensors, the event is loud and unambiguous. On the surface, a P-8A Poseidon Maritime Patrol aircraft that has been orbiting at altitude, coordinating the operation, captures the surfacing on its sensors. Exact position, exact time, hull silhouette, full acoustic record of the emergency surface sequence. The Virginia does not surface. It logs its data and resumes its patrol. There are no casualties in this engagement. No names, no flag-draped coffins, no press releases. Just a diesel submarine riding the surface in heavy North Atlantic swells, 60 miles south of Greenland, with a crew that is alive and a mission that is finished, and somewhere in a database, a new acoustic signature file. Complete. Verified. Matched to a hull type, a patrol area, a specific battery discharge curve that is as unique as a fingerprint. What do you think? Did this outcome accomplish more than a sinking would have? Drop your answer in the comments. We read every one. Here is what this engagement reveals about the layer cake, and it is the detail that sticks with me every time I go through the sequence. The diesel submarine's crew made no mistakes. They chose the right depth, the right speed, the right season, the right thermal profile. Their tactics were correct. The layer cake worked exactly as physics promised it would, against every sensor firing from outside the water column, against surface ship sonar, against sonobuoys dropped from above, against active pings fired downward through 3 thermal boundaries. The layers scattered all of it. What they could not account for was a weapon that does not fire from outside, a weapon that enters the column, descends through every boundary, and searches horizontally from within the deepest layer. The same thermal boundaries that made them invisible from above offered exactly 0 protection from a Mark 48 that was already below them and closing at 1,400 meters per minute. Here's the counterintuitive truth about thermal stealth in cold water. The layer cake is not a shield. It is a trap with one door. That door is vertical entry from above, a weapon that can be guided through the boundaries, that carries its own seeker, runs its own active search, and stays connected to a human operator by a wire transmitting real-time data. Does not use that door at all. It enters from the side, at depth, and the boundaries are irrelevant. The submarine chose a hiding spot optimized against one attack geometry. The Virginia chose a weapon optimized for the other. And the wire is the detail most people miss. The wire-guided link between the Mark 48 and its launching submarine is not a relic of older technology waiting to be replaced by autonomous guidance. It is a deliberate design choice, kept through every upgrade cycle, because it keeps a human in the decision loop until the last seconds of the engagement. The operator on the Virginia could have detonated, could have commanded the torpedo to run its final attack sequence at any point after the close pass maneuver. He chose not to. That choice, to shallow, to pass, to record, to transmit a single identifying ping, is not something an autonomous weapon makes. It is a judgment about strategic value versus tactical opportunity, made in real time by a human being who had all the information and the authority to act differently. That wire is 20 nautical miles of copper and fiber, spooling out behind a torpedo moving at 55 knots through cold water. It is also the difference between a weapon and a decision. Before we close, one thing about the Mark 48 ADCAP that almost nobody mentions in the popular coverage: the torpedo seeker does not lock onto a sound. It locks onto a combination of characteristics: hull resonance frequency, propulsion noise signature, flow noise at speed, and for a submerged target, the Doppler shift profile of a moving object displacing water. When the diesel submarine went to emergency power and turned, it did not just make more noise. It changed its Doppler profile in a way that is, functionally, a confession. A stationary decoy emits sound but creates no Doppler. A moving hull does both. The ADCAP's computer weighs the two returns, assigns confidence values, and the decoy gets dismissed not because it sounds wrong. It may sound exactly right, but because it does not move right. You can fake sound. You cannot fake motion. That is why thermal layers, decoys, and sprint and drift tactics all fail against a close-range wire-guided seeker with current generation processing. The physics that hid the diesel boat from the surface was real and correct. The weapon sent to find it was designed by people who understood that physics just as well as the submarine crew did, and built a hunting system that operates inside it instead of against it. The layer cake did not fail. It worked perfectly. for everyone except the submarine it was supposed to protect. If you want to see how a P-8A Poseidon coordinates a multi-asset anti-submarine hunt across a full ocean sector, the sonobuoy fields, the MAAD passes, the Link 16 data handoff to a surface group, that breakdown is coming. Comment ONU if that is the next one you want. And if the physics of wire-guided torpedoes is the kind of detail that kept you watching, hit subscribe. We build these for the people who want to understand how the systems actually work, not just what they cost. Stay with us.